Hello everyone, today is day 44 of solving a LeetCode problem every day, and today I'm going to be solving LRU Cache, which is a least recently used cache. So design a data structure that follows the constraints of a LRU, implement the LRU Cache class, so we got to create the constructor, which initializes a cache with a capacity, and we have to implement a get method that returns the value of the key if the key exists, otherwise return -1. Then we have our put method, which updates the value of the key if the key exists. Otherwise, we just add the key value pair to the cache, and if the number of keys exist the capacity from this operation, evict the least recently used key. And what makes this problem a little difficult is the fact that the functions get and put must each run in O of 1 average time complexity. So to start out, what is a cache? So traditionally or typically, when you store data, you usually do it to a disk. And the reason why you do it to a disk is because, first of all, it's a lot cheaper than storing data in RAM. So usually when you're thinking of storing, like if you think of your computer, you might have like 64 gigabytes of RAM or 32 gigabytes of RAM or something. But when you're thinking of your disk, you're more thinking in terms of like I have a terabyte of data I can store on my disk. So that's one reason why you might store data in the disk. And the second main reason why you store data in the disk is the fact that data is persistent in your disk. So if you restart your computer, you don't just lose all the data that was stored on your computer. It's persistent. However, any data in your RAM gets reset every time you reset or restart your computer. And a cache is typically going to be stored in your RAM or in your memory. So the reason why caches are used is because it's much faster to read and write elements from memory rather than doing it from your disk. So it's generally just an accepted fact that it's much faster to do it from memory. So that's the reason why a cache is used. It's to optimize your application, and you can make read and write operations faster. So that's one. So that's where I'm going to start. That's kind of where I started out, just giving a little background on what a cache is. A least recently used cache is it just means that our cache has some type of capacity, and once we hit our capacity, there's different ways of maintaining our cache. So the way we're doing it is by removing whatever the least recently used element was and putting the new element in there. Another option would be to, like, for example, remove whatever the first element that got it added into the caches and add the new element in. And there's a bunch of different ways to do it, but the way we're doing it today is the least recently used way. So to start out, our cache is just going to be a hash map. So this is going to store our keys as our keys, and as values, I'm going to get to what values are going to be stored in just a second. But what makes this problem a little difficult, I guess, is the fact that we have to find a way to remember whatever the least recently used element was, and we have to be able to do these operations in constant time. So, one thing you might think of is maybe creating a queue with an array, or not like a queue, but just kind of having some type of array structure that basically just maintains the ordering of whatever, the least recently used elements are. Like, for example, if you can have like an array like 1, 2, and 3, and when you get 2, you might remove 2 from the middle and add it to the end, and now 2 was the element that was last used. But the problem with this is that we need to every time we perform a get or put operation, we have to update the structure, because when we put something or we get something, that means we just used that element in the cache, which means that we just used it. So now we have to update this array, since now that element is the last used element, not 3 anymore. And if we have an element in the middle, so I just did this. So we started out with 1, 2, 3, and we just say that we just got 2. So we want to say that it's now the least use or the last use element. For us to do that, we have to remove an element from the middle of the array. And for us to do that, that means we'd have to shift the rest of the array down. And that means that this would run in linear time complexity. However, it says here that a requirement is that get and put must each run in constant time complexity. So an array is not gonna be what we can use. What we can actually use is a linked list. So let's say we had 1, 2, and 3. You know, if we want to add a new element in, it's just as easy as adding it to the end of the array. And let's say we have this element in the middle, let's say 2, and we want to update this. What we're going to do is we're going to store. So I remember when I said we're going to talk about what the value is going to be later. So as the keys, we're going to have the actual keys as keys, but the values are going to be the nodes themselves. So we're going to be able to access the nodes in constant time using the cache. So let's say we want to update 2. What we can do is we can remove 2. So now like 1 would now point to 3, and 4 would have 2 after it now. But there's gonna be one more thing that I'm gonna do. I'm gonna have 2 dummy nodes. So there's gonna be a head node and a tail node. And what I'm also gonna do is, instead of making this a singly linked list, this is gonna be a doubly linked list. So not only are there gonna be next pointers, but there's gonna also be previous pointers. So now whenever we want to, so remember how with the linked list, I was saying that we want to add elements to the end of the list to signify that that element was the last used element. So for example, I might want to add a 2, but the problem is, you know, every time we maintain, for us to be able to add elements to the end of this linked list in constant time, we'd have to maintain a pointer to the head and a pointer to the tail. But it might be confusing to implement that logic in code. So what we can do is add this dummy head node and dummy tail node. And this head node is always going to be the head. This tail node is always going to be the tail. And since this is going to be a doubly linked list, every time we want to add an element to the end, we can just set the previous element of the tail to now be that new element. So it makes adding elements really easy in constant time. And getting elements is also going to be in constant time since we're just grabbing it from the cache. And yeah, so I mean, I don't want to get into too much detail about like how this is going to be implemented, just because this problem I feel like is a little bit comprehensive. Like there's a lot that needs to be done, and I don't want to make this a super long video. So let's just get straight into the code. So to start out, we do need to create a node class since we're going to be creating a linked list. And this node class is just going to, so within the constructor, we're just going to pass in a key and value, and the self.key is going to be key, self.value is going to be value, and then self.next and self.previous is just going to be equal to none. And then next we want to handle our constructor for the cache itself. So we already created the cache, but now we need to create our head node and our tail node. And to start out, we want to set our head.next to be our tail and our tail.previous to be our head. And then we want to also maintain a reference to our capacity. So we're going to say self.capacity is capacity. Now, I'm not going to worry about these methods yet. What I'm going to create are 2 helper methods, and this is going to be an insert or a put and a remove method. Or sorry, an insert and a remove method. And these methods are going to be specifically for adding and removing nodes from our linked list. So to remove a node from our linked list, what we're first going to do is, since this method takes in a key, we're going to grab the node from the cache. And then we're going to grab the next node and the previous node, and that's just going to be node.next and node.previous. And then we're going to set the previous node.next to be the next node, and next node.previous to be the previous node. And then node.previous and node.next are gonna both be equal to none, so we just clean up those pointers. So if we have a list, what we're doing is we're taking this previous node and setting its next pointer to be the next node, and the next node we're taking its previous pointer and setting that to be the previous node, and that's pretty much how we just get rid of that node in the middle. Now for the previous node, for the insertion method, it's going to be super similar. I'm going to get into why in a second, why a node is being passed into here instead of a key. But what we're just going to do is say self.tail.previous.next is going to be equal to node. So we take the previous node to the tail's next pointer and set that to be the node. And node.previous is going to be the previous node from the tails. And then we're going to set self.tail.previous to be this new node. So now it's the last used element. And then node.next is just going to be equal to self.tail. Cool. So that's our insertion and our removal methods, but now we have to implement our get and put methods. So for our get method, the first thing we're going to do is check if the key is in the cache. And if it's not, we can just return -1 because that's what it tells us to do. It says right here, if the key doesn't exist, return -1. So in here, we're going to remove the node from the linked list. And the reason why is we're going to insert it back in. Because this insertion method right here, it always inserts nodes into the end of the linked list. So basically what we did is we removed the node from the middle of the linked list, and now we added to the end of the linked list to say that this node is now the last element that was used. And then we're just going to return whatever the value is. So when we grab the key from the cache, this would return a node, and we want that node's value as what's being returned. So for our put method, this one is going to be a little more complicated, but it's still going to be pretty simple. We check if the node is in the cache, and if it is, we want to remove it because, again, we want to update this new key to be the last recently used key. Now we're going to create a new node. And the reason why we're doing this is, remember earlier when I said I'm going to talk about why a node is being passed into here instead of a key? The reason why is in our get method, when we remove a node, we always know the node is going to exist inside the linked list. So we can just pass in the key. But when we're inserting a new node into the linked list, it's not guaranteed that this node already exists in the cache. Because like for example here in our remove method, we can pass a key and just reuse the same node that was in the cache. But in our insert methods, it's not always guaranteed that this key already exists in the cache. Sometimes we might be updating something that already exists, but sometimes we're just going to be adding something that hasn't already existed. So in that case, we have to create a new node, and then we can just insert this new node. So self.insert new node, and then to the cache, we're going to set this to be the new node. So if this key already existed in the cache, would be updating the old node with the new node. And then we want to check if the length of the cache is greater than the capacity. And if it is, we want to grab the least recently used element, and that's always going to be the element in the beginning of the linked list. And then we want to remove that. So we're going to pass in the key of this element, and then we're going to delete it from the cache. So that should be it for the problem. So if I run this, it's accepted. And if I submit this, it's accepted. So as for the space complexity for this problem, is going to be linear, since the amount of space we need is going to be proportional to whatever our capacity is. And the time complexity of this is going to be So it's going to be dependent on the method, but I mean, remove method is constant time. Insertions is also going to be constant. Get and put are also going to be constant. I mean, the way we implemented this was supposed to run in constant time. So I mean, all these methods are constant. So I mean, like for example here, we're not iterating through anything. We're just performing a constant amount of operations. The same thing here, and the same thing with these two methods. So yeah, that's my solution for the day.